All right, well, welcome to the BC Notes for 2.6. We're going to look at area bounded by a polar curve, and we're going to spend, I think, like 3 or 4 days on this. So today's day 1. All right, so to find the area of a polar curve, you might remember that to find the area of a sector, we found a fraction of the area of the sector. This is kind of the formula that you probably saw in geometry. Area of a sector was measure over 360 times pi r squared. Now keep in mind, we're not using 360 degrees. We're not using degrees as we talk about our circles. Instead, we're talking about 2 pi. 2 pi. So instead, if I replace this 360 with 2 pi, and we usually reference our angle measure as theta when we're talking about radians rather than m, which is a more common unit of measurement when we're talking about degrees, then I'd have theta over 2 pi times pi r squared. Well, the pi's cancel out. And so we have this formula here where I've got theta over 2, or 1/2 theta, times the radius squared, which sometimes is commonly written like this. And that's for the area of a sector if we're looking at this in radians instead of degrees. Now imagine that what we want to do is we want to take something that's not just a circle, but it's a curve. Okay, so we're looking at a curve, which might have all sorts of different changes and may not be perfectly circular. But maybe we divide up the area into a whole bunch of regions. Each region could look like the area of a sector of part of a circle, particularly if we made them small enough. And if we create smaller and smaller sectors, so we increase the number of sectors that we have, then we could actually then use an integral here. I'll let you kind of look through some of this on your own, but keep in mind the summation, if we have an infinite number of shapes, is really our definite integral. It is our definite integral. This right here is our radius. And so you might notice how this compares 1/2 of the function squared d. Theta would be your delta theta. And that is our angle. Why is the angle theta now delta theta or d theta? The reason is because if theta were the entire angle, maybe from here to here, and we're going to go ahead and we're going to split this up and make that angle as small as we can. We're going to try to create an infinite number of sectors inside here and accumulate them, which is our definite integral formula. So this, when we increase the number of sectors, becomes this. And the 1/2 can be pulled out front as a constant multiplier. This would then be 1/2 times the definite integral from alpha to beta of the radius squared d theta. And what this helps us find is the area bounded by one polar curve, where the radius could also be called f of theta. And alpha and beta are different angles on our unit circle. So where are we stopping and where are we starting in our calculation of the area here that we want to find? And again, this area is bounded or outlined, if you will, by one polar curve. Now we're also, as time goes on, going to be look about what if the area is bounded between two different polar curves. So like maybe I have like a cardioid, for example, and I also have a circle, and I want maybe the area between them on a certain region. Like maybe I want the area between them from here to here, maybe going around the long way. Maybe I want this. Okay, well, we're going to say that we have two different polar curves, and they each have a different radius. One of them has radius capital R, one of them has radius lowercase r. And what we're going to say is that this capital R would be your area or your radius that is farther from the origin. And this radius would be the radius that is closer to the origin, or the smaller radius. Why would that matter? We're going to represent area between two curves as a positive value. And so by taking the radius squared of the larger one, the one that's farther away from the origin, minus the one that's closer, the smaller one, we're going to end up with a positive. Now, why are we subtracting? I'm going to actually go to the idea of a thermometer for a second or something. Like, let's say that I am starting at 10 degrees Fahrenheit and I am ending at like negative 3 degrees Fahrenheit, and I want to find out the number of degrees between them. Well, to do that, I would subtract those. And the number of degrees between them is 13 degrees. So when you're trying to find out what's between two things, you subtract them. Here's another way to think of it. If I had the entire area of the big polar curve, in this case, the cardioid, remember I had wanted the area between. That's too big. If I look at the area that was bounded by the circle, that's too small. And that's actually the wrong area. I want maybe this yellow area. Well, imagine if you were using a cookie cutter. You're cutting out cookie dough. And you cut out this cookie dough in the shape of a cardioid. Okay, you have that sitting on your table. And then use a different cookie cutter and you cut out a circle. And then you lifted out the circle and you ate it, which is what I would do. Okay, or you cooked that cookie. What would be left on your table? It'd be this. It'd be that dough or that area that was between the two shapes. Man, I just got to tell you, that's some good drawing. I'm sorry. Very embarrassing. Okay, but that's essentially what we're doing. That's why if it's between two curves, we're going to subtract. Okay, let's take a look with some specific examples. There's your formula again if we're bounded by one curve, which is where we're going to start. So let's say I've got this graph. R is equal to 2 plus 2 sine theta, and we want to find the area bounded by the graph. Well, the form of this polar curve is the form of a cardioid because A and B, these values right here, are the same. This is a cardioid. If you're having a little trouble with that, you can always stop. Notice that this is not calculator active, and you can choose your quadrangles and plug them into your formula to find the radius. So the quadrangles would be your 0, pi over 2, pi, and 3 pi over 2. If you felt like it, you could go back to 2 pi, but that's the same as 0. So 2 plus 2 times the sine of 0. Sine of 0 zeroes out. This is 2. Since the sine of pi over 2 is 1, this next one will be 2 plus 2, which is 4. Sine of pi zeroes out, leaving me with an output of 2. And the sine of 3 pi over 2 is negative 1, which zeroes out. 2 plus 2 times negative 1. So in the direction of the 0 degree angle, I'm going to go 2 units. In the direction of pi over 4, I will go 4 units. In the direction of pi, I will go 2 units. In the direction of 3 pi over 2, I go 0 units. This is my cardioid. Here's basically what's happening with this shape. Kind of like a circle with a dip. Where that 0 is, that's where we dipped in. This is going to be symmetrical around the sine axis, around the y-axis, pardon me, because it's a sine function. Sorry, mine is not super symmetrical. It's a good thing we're not judged on the skill set of the drawing, because I think like a little bit of a fail here for me. But there we go. Oh, wow. Maybe that was okay. Now, we want to find the area bound by this graph. Now, there's more than one correct answer. But I will tell you there's one answer that's way more common than any other. The area formula can be found by doing 1/2 times the definite integral from 2 different angle measures as I move around the circle and times the radius squared. Well, what is the radius? This is the radius. You can see it even equals r. So this is the function I'm going to be using. D theta. Oops, sorry. What about the angles? Well, my angles actually, kind of if you look at where the symmetry of this is, kind of starts here and goes up to the top and then kind of repeats again. One way to do this is to say, hey, it goes from like negative pi over 2 all the way around to 3 pi over 2. That's one way to kind of think about this. Often what I do is I go, well, you know what? The left side and the right side are going to be the same. So I'm going to calculate this from negative pi over 2 up to pi over 2, and then I'm going to double it. Because what this would be is this would be twice the right side. Why do I like to do that? First of all, then I don't have to deal with this fraction. Also, I usually then I'm working with angles that I'm a little bit more familiar with. The negative pi over 2 and the pi over 2 are a little bit easier for me to evaluate. Oh, I forgot something really important. This is squared. So I want to have my radius squared right here. And so evaluating this is actually a little bit less common. Most of the time they have you write it. So quite often you might see answers like this, like if this were multiple choice, this might be a common answer. But again, we could have seen 1/2 of, and then change our angles to go all the way around. Now, why did I start at -pi/2? I started there just because that kind of is where the dip in the graph is. Oh, I should add my differential there at the end, d theta. That's why I started there. What about if you went from 0 to 2 pi? If you went from 0 to 2 pi, would that work? Well, let's see. If I start at 0, I'd fill out from here to here. And I kind of, this is kind of like this, all my collection of all my radii that would make these. There's to pi/2. Now I'm continuing along as I go to pi. And then as I move past pi, now I'm at 3 pi/2 and getting to 2 pi. Sure, that also would work. Well, what if I tried to use like 0 to pi? 0 to pi, let me take out these little fans in here. Oh, I erased the whole function. How sad. My daughter is literally laughing at me in the other room. What if I tried to do, again, like twice one of the halves, and I wanted to do it from like 0 to pi? Let's take a look and see if that would really be a half of the graph. If I started at 0, I'd go to here, and then if I fan out with all the radii, here's 0 to pi/2, continuing around to pi. Now the question is that really half of the graph? I think visually we can tell it's actually not. So this is not going to work with those angles. If I want to do twice one of the halves and double one of the halves, oh, by the way, I would have forgotten my 1/2 anyway, right? Lots of things wrong there. But this doesn't work with those angles. That's a no. So instead what we would need to do is we would need to make sure that we pick a half where it's actually got that symmetry. So I did, when I did twice one of the halves, that's why I picked -pi/2 to pi/2. Certainly not the only half. Another half that you could do is you could do twice 1/2. Remember, the 1/2 is part of the formula, but I'm doubling a half to get the full amount. I could have also chosen to do the left half, which went from pi/2 down to 3 pi/2 of my radius squared. Squared d theta. One other thing I want to mention that is often something that students kind of wonder about is, why did I name, let's say I was doing the yellow side, twice the yellow side. Why did I name this as -pi/2 and not 3 pi/2? That's actually a really, really good question. If I name this as 3 pi/2, and then I go to pi/2, it's actually going around this way. Is that wrong? No, it's not necessarily wrong, but when we kind of go around directionally that way, you might remember, like the whole idea of accumulation. If we're talking about accumulation in AB, we're talking about from right to left. I'm sorry, from left to right, just like we read and we're accumulating area, we're like adding on area. If we go from left to right, you might remember you have a sign change. Well, when we're talking about polars, we like to go to the smaller angle to the larger angle, not the other way around, otherwise you get a negative area. Okay, just like if you've got your intervals here upside down, you get that negative area. So I am going to be careful here to try to use the correct one. Now we still, by the way, haven't solved it. You might notice all I did was set it up and show you some different ways it could be set up. So let's work on the solving, which is kind of painful a little bit on this one. I'm going to go ahead and expand this out. Let's think about our strategies for solving integrals. I do have u substitution, but if I let u equal that inner function right here, du would equal to cosine of theta d theta, and there is no way to replace du. That's not in here. So u substitution fails. I can't use partial fraction decomposition. I don't have a fraction. I'm not doing integration by parts here. I've really kind of got the same thing multiplied by itself, and it's really more of a foiling situation. So remember, in case you're curious where the 1/2 goes, because I did twice the right side. All right, so I did not go all the way around the circle. I just went halfway around the circle. Okay, and I was strategic about making sure I chose a half that was where the symmetry was. So I'm going to expand this out through FOIL, and I would get 4 plus 8 sine of theta plus 4 sine squared of theta d theta. Now, most of these terms I know how to actually integrate. I know how to integrate 4. I know how to integrate 8 sine theta. What I don't know how to integrate is 4 sine squared theta. But thankfully, we do have some nice trig identities. Hey, there's our YouTube page that we can use to get this something that we do know how. Let's see if I can get a good image here. So that we can find something that we do actually know how to integrate. Let's see if I can find the one I want. And we're getting close. Let's see, here we go. All right, so remember what we have here is we have this 4 sine squared theta. We have this 4 sine squared theta. And something that I want to do is I want to try to rewrite this as something that's not sine squared. It's the fact that the trig function is squared that's going to cause me problems when I'm trying to integrate this. So you might notice, let's see, that I've got some double angle formulas here. Let's see, actually, I'm going to pause real fast and get a better screen. Hang on, I'll be right back. Okay, back. Sorry, hopefully you can see this a little bit better. That was, my screen was, it was a little fuzzy there. So you might be wondering, what am I looking for? Now remember, the thing that was causing me a problem over here was the sine squared. Like, how am I going to handle that sine squared? Well, if I look at some of my double angle trig identities, I do have one that has a sine squared. 1 minus 2 sine squared of x is equal to cosine of 2x. Well, I can manipulate this a bit, and I can isolate my sine squared. Let's see, let me do some moving around. I'm going to move this around. So twice sine squared of x is equal to 1 minus the cosine of 2x. Therefore, sine squared of x, or sine of x quantity squared, notice the function's being squared, not the argument, is 1 minus the cosine of 2x all divided by 2. This, there are very few trig identities actually that you have to know in calculus. You need to know your Pythagorean ones, and you need to know this one. This one's super helpful. And so this one will show up in this type of problem a lot. We'll get this quite often with cardioids. We'll get this type of answer. So what I'm going to do is I'm going to replace sine squared with 1 minus the cosine of 2x all divided by 2. So I've got the definite integral from negative pi over 2 to pi over 2 of 4 plus 8 sine of theta plus, now I'm doing 4 times all of this. Well, 4 times that 2 on the denominator would be 2, and I'll distribute it into this numerator. 2 minus 2 cosine of 2x, 2 theta, d theta. And I could simplify this if I'd like. This is the definite integral from negative pi over 2 to pi over 2 of 6, when I combine like terms, plus 8 sine of theta minus 2 cosine of 2 theta d theta. Let's integrate that. All right, so this would become 6 theta minus 8 cosine of theta. Now be careful here. We have a function within a function. The derivative of 2 theta is 2. I need to undo that derivative by multiplying by 1/2, which would then divide out with this coefficient. So this would be minus 1, and then the integral of cosine is sine 2 theta. And then all of this is evaluated at pi over 2 and at negative pi over 2. So I would have 6 times pi over 2, which would be 3 pi, minus 8 times the cosine of pi over 2, which zeroes out, minus the sine of twice pi over 2, which is the sine of pi, which zeroes out, minus, all of this is now going to be evaluated at negative pi over 2, so 6 times negative pi over 2 is negative 3 pi, and then cosine of negative pi over 2 is 0, and sine of negative pi is 0. So I end up with 3 pi plus 3 pi, and my answer is 6 pi. But this trig identity is not something that's probably on your radar. So you are going to want to take good note of that. There's no reason for you to rederive that every time and re-isolate. So I would just use that the sine squared of x is equal to 1 minus cosine of 2x over 2. Now this next one, you do not have to evaluate by hand. We just have to set it up. And then we have to use our calculator to find the area. Now you might notice we have a couple here that are dealing with petals. That's because petals are harder to graph. Now we're only going to use the calculator to find the area. Quite often you might have to set up the integral without using a calculator, so you need to know how to do that without the calculator. So what does this look like? Well, I can tell that this is going to be a rose, and the length of each rose is 2 because that's the constant multiplier in the front, and there'll be 3 petals. Remember, when the number multiplying theta for this argument here is even, then it's twice that many for the petals. To find out where these petals start and end, I'm going to take this radius and set it equal to 0. I want to see where I go back and touch the origin. So I want to look for where is the sine of 3 theta equal to 0. Well, sine is equal to 0 when the angle is at 0, when the angle is at pi. Now I'm going to go around the circle a couple times, 3 times to be exact. When the angle is at 2 pi, when the angle is at 3 pi, when the angle is at 4 pi, and when we're at 5 pi. All right, so my petals are going to be zeroing back around here. If I divide each of these by 3 at 0, at pi over 3, at 2 pi over 3, at pi, at 4 pi over 3, 5 pi over 3. And I guess if I went back around all the way to the end, that would be at 6 over 3 and 6 pi over 3. Sorry, dogs are having fun, which is 2 pi. Now, what this is going to do, since this is odd, we're going to actually have more kind of little intervals here than I actually need. I'm going to just draw in some little dots here. This is going to zero out at 0, at pi over 3, at 2 pi over 3, at pi, at 4 pi over 3, at 5 pi over 3. Notice there's 6 intervals, but there's only 3 petals. So where am I actually having some area? You could plug in a value here if you wanted. Like if I plugged in maybe a value like pi over 2, for example. 3 times pi over 2 is 3 pi over 2, which has a sign of -1, times 2 is -2, which is in this direction. Here's one petal. And basically what they are is they're going to be every other region. So it looks like this. Oh, okay, my radius is 2. Let's see if I can get my radius to kind of look like 2. I got some petals I got to fix. Let's see if I can fix that. This circle is not part of the answer. This is just a technique for drawing. Okay, I'll get rid of the circle. All right, there it is. So I want to find the area of one petal. Now, it is really important. You can pick any of these 3 petals that you want, but it is very, very important that you actually pick a region that actually has a petal in it. Otherwise, you're gonna get it, not something that's very valid. Remember, area can be found by doing 1/2 of the definite integral from alpha to beta of the radius quantity squared, d theta. Ooh, almost forgot my squared. You can pick any petal you want. I'll do this one. I will do, and that one goes from 0 to pi over 3. And notice that those are going to be those values that I found here when I figured out where the area of this equals 0. Now, how do I enter this onto my calculator? So I'm going to do 1/2 times the definite integral. So shift plus. I went from 0 to pi over 3. Your pi button's right here. So pi over 3. And this was of twice sine of 3 theta quantity squared. So 2 sine of 3 theta. Where's theta? Right here, actually. But you could use x. Doesn't matter. The calculations are the same regardless of what variable you use. So Don't stress yourself out if you don't want to use theta. I just am showing you where it's at in case you'd like to use it. And let's calculate this. We get pi over 3 for our answer. All right. Example 3, sketch and set up an integral expression to find the area of one petal of r is equal to 4 times the cosine of 2 theta. This is helpful when they say one petal because then you know it's a rose. We're not going to evaluate it, and let's do no calculator on this one as well. Okay? All right. Well, this one will have a radius of 4. Not even on my scale. Super sorry. Okay, so I'll erase this circle later. This is just to help me draw kind of the right length for each petal. And I would like to see where these petals are going to start and end. So I'm going to set the radius equal to 0. So the cosine of 2 theta is 0. Well, when does cosine equal 0? That happens at pi over 2, at 3 pi over 2. And I'm going to go around the circle twice because this is 2 theta, at 5 pi over 2, and at 7 pi over 2. So if I divide each of these by 2, theta is at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. This is where I'm going to zero out. So I'm going to draw on these dotted little radii here to kind of help me understand that that's where I'm going to the origin. And my petals need to be symmetrically placed inside of this. Because this is an even multiplier for theta, I have twice as many petals. I have 4 petals. I also have 4 regions, which means I have 1 petal for each region, and they look like this. And again, keep in mind this circle on the outside of this is not part of the graph. It was just a graphing tool. I want to find the area of one of these petals or set up an integral for it. There are, goodness sakes, I could think of 13, maybe 14 different ways, 14, 15, to write a correct answer here. We're not going to go through all correct answers, but I'll show you a few. One way is to go ahead and say, where does this petal, this yellow petal, start and end? And I could do the area is 1/2 of the definite integral of my radius, 4 cosine of 2 theta, quantity squared, don't lose the squared, d theta. Well, this one starts and ends at like 7 pi over 4 to pi over 4, but we're not going to think of this as 7 pi over 4. I want it to be a smaller. I'm going to think of it as negative pi over 4 to pi over 4. And that stresses kids out with that negative angle at the beginning. So what if instead we just did this top half? And we recognize that that top half could be doubled. So you could do twice times 1/2 times the definite integral from 0 to pi over 4 of 4 times the cosine of 2 theta quantity squared d theta. And then these cancel out. This is actually how I prefer to write it. We could have also done twice the bottom half. We could have done that with any of these other petals, a full petal, or we could have done twice the top or twice the bottom or twice the right, twice the left. However you would like to think of that. This is a pi over 4. That is very illegible. If these are multiple choice, I think you're kind of more likely to maybe see that one, I would say. All right, this next one is our last one. We're going to sketch and set up an integral expression to find the area of the inner loop. Okay, there's a hint here. This is a limacon with the inner loop. Remember, this could also be pronounced limacon, limacone, limacone, lots of different ways. But this one has an inner loop. How do you know? It's because in this situation, A is smaller than B. Again, this might be easiest to graph if you use the quadrangles. I think for cardioids and for limacones, it's easy to use those cardioids or use those quadrangles. So I'm going to use 0, pi over 2, pi, and 3 pi over 2 to help me out with this a little bit. You could also use 2 pi if you felt like it, but it's the same as 0. So if I plug them in, the sign is 0, 0, so this would be 1. Sine of pi over 2 is 1 times 2 plus 1 is 3. Sine of pi is 0, so that zeroes out, leaving just a 1. Sine of 3 pi over 2, be careful, is negative 1 times 2 is negative 2 plus 1 is negative 1. The inner loop is going to be coming from where we dip into the negative radius here. All right, so when we have a 0 degree angle, we're going to move 1 towards that, or 0, not degree angle, an angle of 0 in the radians. At pi over 2, we're going to move 3. At pi, we will move 1. And at 3 pi over 2, we have -1. There's the inner loop. What does this look like? This looks like this. It's kind of a lot like a limosome with dimple. And there's the inner loop. Now, all we want to do is find the interloop. Do not evaluate. We're just setting up an integral expression. No calculator on this one. So where is the inner loop starting and ending? The inner loop is actually happening where we get a negative radius. It's actually happening like somewhere in this region where we get a negative radius and we're dipping into the quadrant that is directly across from it. And that's how we get the inner loop. So to figure out where this is happening, I again need to see where does this radius equal 0. So I'm going to set this radius equal to 0 and do some solving. So let's see, -1 is equal to twice the sine of theta. I want to look to see where does the sine of theta equal -1/2. Now, this is where, and there's going to be two values, this is where I'm going to have my inner loop start and end. You might remember in our unit circle that for sine, if sine is a pi/6 angle, my ordered pair for cosine sine is √3/2, 1/2. Now, this is a positive 1/2 for pi/6 and 5 pi/6 because those are above the x-axis. As soon as I hit 7 pi/6 or 11 pi/6, this is where I started to get those negative signs that equal 1/2. So theta is actually going to equal 7 pi/6 and 11 pi/6. And so at 7 pi/6 and 11 pi/6, you might notice there's nothing in that region for that part of the cardioid, at least not on this positive side. It's because the radius becomes negative in between those areas. And that's how we form the inner loop. So to find the area, one way you could do, the area is 1/2 times the definite integral. Now you want the smaller angle, 7 pi/6 to 11 pi/6 of the radius 1 plus 2 sine of theta quantity squared d theta. That's one way. Another way is you could do twice, maybe the right side, or you could do twice the left side. I don't know. Whatever you want. If you do twice one of the sides, I could have 2 times 1/2 the definite integral of from here to here. So that would give me this side of the inner loop. I guess it's actually twice the left. It kind of goes backwards straight across, okay, like 180 degrees or pi across. And so this would be from 3 pi/2 to 11 pi/6 of the radius squared, d theta. And then again, the 2 and the 1/2 cancel out. I could also do twice the right. And I could have done 2 times 1/2 of the angles in this region, which would give me the right side that I just colored blue. And now you can't see. Let's keep that yellow. And so that would be the definite integral from 7 pi/6 to 3 pi/2. That's where that symmetry is, of 1 plus 2 sine of theta, quantity squared, d theta. And then those cancel out. Which answer is better? They're all considered equally correct. What would be more likely to show up on a multiple choice? Who knows? What will I accept? All of the above, and a free response question. All right, that is the end of our video for 2.6. Thank you very much.